Thanks for watching my presentation of our paper, Experimental Study of Flame Spread Underneath Photovoltaic Modules. I'm Kristensen, a PhD student from the University of Edinburgh. As the title reveals, the research is related to photovoltaic installations, a type of renewable energy which has increased rapidly during the last decade to a total global production of more than half a terawatt in 2019. A way to utilize this new technology is to use unused flat roof constructions, such as this refrigerated warehouse in Norway. The issue is that a PV installation is a large direct current system, which increases the probability of ignition and thus PV-related fires. Merton and McManee recently published an overview of the globally known PV-related fires in 4 countries. It is noticed that Italy has significantly more fires than the other countries, which has to do with the way their data is obtained rather than the actual number of fires in the countries. From my point of view, it's more interesting to look at the annual number of fires per megawatt installed capacity, which certainly brings Australia level with Italy. Taking that analysis even further, a weighted mean value with respect to the number of fires gives an annual rate of 0.029 fires per megawatt, which is equivalent to around 18,000 fires per year. The overall problem can be broken down into 2 sub-problems. First of all, it's an increased probability of ignition, as it is a large direct current system with poor installation practice and a lack of standardization. But it's also a physical barrier installed on top of the roof. It is a modification of the fire dynamics, and it alters the consequences in case of ignition, no matter the source of ignition. And since the roof construction should be able to withstand any kind of ignition source, the fire dynamic issue is the topic of my PhD and thus this presentation. A bit simplified, the problem can be condensed into the following. If we have a normal open roof construction and ignite a wood grip on top of it, it will heat up the nearby roofing membrane, which will release pyrolysis gases and ignite. However, the fire will not propagate, as both ignition of and heat release from the roofing membrane is suppressed by the presence of flame retarders. That is because the roofing membrane is classified according to specific standards. The interesting thing is that if we take the same roof construction and the same wood grip, but install a PV module above it, the flames will deflect below the module and thereby heat up a larger area with a higher heat flux. As a result, the roofing membrane will release a higher concentration of pyrolysis gases and, as a consequence, suppress the flame retarders, whereupon the fire can grow below all of the PV system. The fire dynamic system, consisting of the roof construction, the PV module, and the ignition source, is highly complex, as it is hard to separate the influence of the materials from the influence of the PV module and the changed geometry. That is why we decided to decouple the complex materials from the geometry to understand how the panel as a physical barrier affected the flame spread. In that way, we turned a very complex problem into a less complex problem. That is why we decided to replace the roofing membrane, which is not representative for all membranes, has a bunch of unknown parameters and is flame retarded, with a sheet of black PMMA, which has well-known properties and an assumed absorbance of 1. In the same way, we decided to substitute the PV module, which is not representative for all modules and does have a combustible backsheet with a black bloody surface, which is non-combustible, reusable, and has well-known properties. In that way, we were able to understand how the geometry affected the flame spread rate, if we increased or decreased the inclination of the panel, or if we increased or decreased the gap height between the PMMA and the stainless steel. In our paper, we wanted to understand how the presence of a horizontal panel and the gap height between the panel and the PMMA affected the heat flux towards the PMMA, and thus the flame spread rate. And then we are back to a very well-known man who defined the fundamental equation of fire spread, where the net energy per unit area per second is equal to the fuel density times the flame spread rate times the difference in enthalpy. The right side of Emmons' fundamental equation were expanded by Quinturi, who also concluded that conduction could be neglected for thin fuels, whereupon the net energy heat flux consisted of the combined conductive and radiative flux towards the controlled volume minus the radiative heat loss. In Quinturi's thermal model for surface flame spread, some values were constants, or assumed to be constant, and some values were variables. To monitor the variables, we designed the following experimental setup, which consisted of a sheet of PMMA installed on top of an insulation board. To prevent flame spread along the sides, ceramic paper were placed on all four sides of the PMMA. The ceramic paper along the left side were soaked in methanol to ensure uniform ignition in all experiments. On top of that, we installed a PV module, which in most cases were substituted by the black stainless steel board. By the use of a lap jack, we were able to change the gap height between the panel and the PMMA. We used a video camera to monitor the flame spread rate and installed a heat flux gauge to monitor the radiative heat flux towards the sample. To measure the temperature of the fuel, we embedded 8 thermocouples into the PMMA. As we wanted to quantify the net heat flux towards the PMMA, the radiative heat loss, and thus the thermocouple closest to the heat flux gauge, was the most interesting. The experimental matrix consisted of 3 different sample widths of PMMA, as previous research had revealed that the emissivity of the flame increased with the width of the sample, which would lead to a faster flame spread rate. However, the majority of the experiments were conducted with a sample width of 30 centimeters, whereas the 2 other sample widths were included to validate the above theory. The numbers without brackets were conducted with the black stainless steel board, whereas the numbers within the brackets were the experiments conducted with a PV module. For all sample widths, a series of baseline experiments were made to validate the experimental setup. As mentioned earlier, all the experiments were conducted with a horizontal panel, as the introduction of an inclination would introduce another variable. Knowing the experimental setup and matrix, we were able to discuss the results, but before doing so, we have to go through the output of the experiments. First of all, we had a lot of video, which made it possible to determine the location of the flame front as a function of time, whereupon we could determine the flame spread rate along the PMMA. We also knew the heat flux measured by the heat flux gauge as a function of time, and since we knew the location of the flame front, we could transform the heat flux as a function of time to the heat flux as a function of distance to the flame front. In the same way, we could determine the temperature of the PMMA at the location of the last thermocouple as a function of the distance to the flame front. How to determine the location of the flame front is therefore a crucial part of the experiment, which is why that will be discussed in the following slides. Before introducing what I personally think is a decent piece of MATLAB magic, I want to show you the difference between a baseline experiment and an experiment with a gap height of 15 centimeters, in both cases for a sample width of 30 centimeters. For the baseline experiment, the length of the pyrolysis zone and the flame height is almost constant. For the experiment with a gap height of 15 centimeters, the first 10 minutes after ignition is similar, but due to an increased heat feedback loop, the length of the pyrolysis zone and flame height increases. As the flames deflect below the panel, the heating of the PMMA in front of the flame front intensifies and the flame spread rate accelerates significantly. To analyze the video, we decided to follow a single line of pixels along the center of the PMMA. By stacking the pixel lines on top of each other, we were able to plot the location of the flame front as a function of time, and we could refine the plot by reducing the time interval. Afterwards, we could identify the relevant data, as everything left and right of the red square were either irrelevant part of the experimental setup or reflections. The top of the square defines the start of the experiment, where the blue part originates from the methanol used for ignition. Everything below the red square were irrelevant, as the flame front had reached the end of the PMMA sample. Finally, we had to transform the distance in pixels into the distance in millimeters. Comparing the plots from the baseline experiment and the experiment with a gap height of 15 centimeters, the difference is clear. To get the location of the flame front as a function of time, we transformed each plot into a binary matrix and located the front of the pyrolysis zone at every second, whereupon we fitted a curve. As we now know the location of the flame front as a function of time for all the experiments, we can calculate the average flame spread rate for the baseline experiments, where it is noticed that a wider sample width causes a faster flame spread rate. If you have read the paper published in Fire Safety Journal, please be aware of the formatting mistake where the order of the sample widths are incorrect. An interesting thing to plot is the relative flame spread rate, whereupon it's possible to visualize how much faster the flame spread rate is compared to the baseline experiments when a panel is introduced above the PMMA as a function of the flame front location and the gap height. In this case, we will look at the relative flame spread rate for the sample width of 20 and 30 centimeters, both with a stainless steel panel, and the experiments conducted with the photovoltaic modules. Please notice that the axes for the relative flame spread rate are not identical. For the higher gap heights of 22 and 20 centimeters, it is noticed that the flame spread rate remains constant, but the presence of the panel results in a relative flame spread rate which is faster than the baseline experiment. When the gap height is lowered to 20 centimeters, a minor increase of the relative flame spread rate is noticed for the sample width of 20 centimeters, whereas it is more evident for the two wider sample widths. Comparing the experiments with the stainless steel panel and the PV modules, the relative flame spread rates are not completely identical. However, the critical gap height seems to be located within the same interval. The trend continues when the panel is lowered even further, and a maximum relative flame spread rate is noticed to be 38 times faster than the baseline experiments, where the gap height is 12 centimeters for the sample width of 30 centimeters. Knowing the location of the flame front for all the experiments also made it possible to calculate the heat flux required to obtain an observed flame spread rate according to the right side of equation 1. And it made it possible to calculate the net heat flux towards a given point according to the left side of equation 1. We used the measured heat flux at the location of the heat flux gates and the temperature of the closest thermocouple to calculate the net heat flux. We compared that to the heat required to obtain the flame spread rate in between the heat flux gates and the thermocouple. To validate the experimental setup, the heat flux required to obtain the average flame spread rate for the baseline experiments are compared to the calculated net heat flux. For the sample width of 30 and 40 centimeters, there is no significant difference between the two heat fluxes, whereas the difference for the sample width of 20 centimeters is assumed to be caused by the fact that the range of the heat flux gates were too high. In general, we deemed the experimental results to correspond with theory. Similar calculations were made for the experiments conducted with the stainless steel panel and the PV modules. For the heat flux required to obtain a specific flame spread rate, there was a decent correlation between the gap height and the required heat flux. However, similar experiments, such as the experiments conducted with a gap height of 17 centimeters and a sample width of 30 centimeters, did not result in the same required heat flux. Looking at the location of the flame front as a function of time, it is evident that the difference is caused by the fact that the transition into a faster flame spread rate did not occur at the same time, whereas the flame spread rate were not similar. If the PMMA sample were longer, it is assumed that the flame spread rate would be similar. Plotting the net heat flux as a function of gap height revealed the same trend, which is also the case for the experiments just discussed. By looking at the ratio between the flame spread rate related heat flux and the net heat flux, there is a relatively clear trend, where the data points for the same sample width were divided into two groups, as seen for the sample widths of respectively 40, 30, and 20 centimeters, as well as the experiments conducted with actual PV modules. The trend is most likely related to the critical gap height, marked with the colored boxes, as the ratio is above 1.2 if the gap height is below the critical gap height, and below 1.2 if the gap height is above the critical gap height. As our net heat flux only accounts for the radiative heat transfer, it is assumed that the lower ratios are caused as the panel as a physical barrier alters the flow of the extraction hood and thereby increase the convective heat loss, which cause a reduction of the flame spread rate. That effect is suppressed when the radiative heat transfer becomes dominant due to the deflection of the flames below the panel. As discussed in the paper, it is assumed that the net radiative heat flux becomes smaller than the heat flux required to obtain the corresponding flame spread rate, as smoke condensates on top of the quartz disk used to protect the heat flux gates. When the heat flux gates is engulfed in flames, the debris is burned away. Reaching the end of the presentation, we can conclude that a critical gap height exists. If the gap height is above the critical gap height, the flame spread rate remains constant and low. But if the gap height is below the critical gap height, the flame spread rate gradually increases until the flame deflects below the panel, which causes a rapid acceleration of the flame front. Small changes in the gap height have large consequences for the fire dynamics. Thus, the consequence in case of ignition below a PV system. Finally, it can be concluded that there is no significant difference between the experiments conducted with a PV module and the experiments conducted with a stainless steel panel. Thanks for watching the presentation. As a last thing, I want to say thanks to the sponsors of my PhD project, IKEA, Rockwell and Kingspan, as well as thanks to DTU Civil Engineering for hosting me as a guest PhD student.